So my name is Rachel Surprenant. I'm a PhD candidate at the University of California, Riverside, and today I'm going to be talking to you all about the sedimentological signatures of mat grounds in the Precambrian, a novel method for their detection, automated detection in remote contexts, and implications for the search for life on Mars. So it's well accepted that in Mars's past, there was liquid water on the surface, right? So this provides the potential for there to have been past microbial life. And when we're thinking about looking for evidence of this past microbial life, a lot of people in this room like to think about signatures of this microbial life that are microscopic or molecular. But as a paleontologist, I'm more interested in macroscopic textural signatures that we can observe in the sedimentological record from standard imagery, right? So to find these types of signatures that could be useful for the search for life on Mars, we can turn to the Precambrian Earth, which is a really useful data set for us to think about how past microbial life expresses itself in the sedimentological record, because it is dominated by a record of organic mat grounds during a time when life on Earth was very simple, right? And luckily, these organic mat grounds formed by a consortia of prokaryotes and eukaryotes, mainly single cellular, have a significant impact on the sedimentological record. We heard earlier today about something called the extracellular polymeric substance that microbes excrete when they are forming a mat ground. It's just kind of this like sticky substrate, and this has an impact on the sedimentological record in that it binds, baffles, and traps sediment that it is living on and within, and thus prevents erosion and stabilizes sediment. In part, this contributes to in carbonate settings, things that you're probably familiar with, like microbialites and stromatolites. But I'm more interested in how this is expressed in siliciclastic settings, which is broadly applicable to the Martian geologic environment, right? And one way that it can be expressed is in textured organic surfaces or iterative organosedimentary surface textures. I'm showing you an example of that up here on the right. That's actually a fossil surface. And they also impact sedimentological packaging in a way that we can identify in cross-section. So when I'm talking about kind of these mat ground biosignatures, I think this brings up a really important question that I want to kind of frame my whole talk in, which is that if life ever existed on Mars, was it ever abundant enough to form organic mat grounds and impact the sedimentological record on a macroscopic scale like we see in the Precambrian? And my answer to that is, I don't know. And the more I think about it, the less I'm convinced that it ever did. But this is still an outstanding question that we need to think about, and there's one way to find out. And again, this is to leverage the Precambrian rock record. So as I mentioned, we have billions of years of evidence of mat grounds existing in the Precambrian, a lot of which is fossil evidence of mats, like what I'm showing up here on the right. These are not great biosignatures for the search for life on Mars, because to identify them, you would need to excavate bedding planes, and it also relies on the fossilization of these surfaces that necessitates a lot of a suite of complex taphonomic or preservational processes that are not guaranteed to have existed on Mars. So instead, I'm interested in looking at the impacts of mat grounds and the extracellular polymeric substance that they secrete on sedimentological packaging, as it manifests as discrete sedimentary structures that cannot occur in the absence of biological mediation. So one of these sedimentological signatures that I'm talking about today are called palimpsest ripples. So I'm showing you images of those here. These are from the Nilpena Ediacara National Park in South Australia, which was recently opened as a national park. Oh, my animations are weird, sorry about that. But if you want to read more about it, it was published a little story about the national park in NASA Astrobiology recently. But palimpsest ripples are defined as stacks of sandstone bedding planes that have rippled bottoms and rippled top surfaces. So we can see if we look at this bedding plane here, there are ripples preserved on the top as well as on the bottom. But what does this mean in terms of like evidence for life, right? we can look at this figure here to see kind of the biological processes behind the formation of these palimpsest ripples. So looking at section B of this figure, when we think about Precambrian ecosystems, microbial mats were ubiquitous within the world's oceans, covering the seafloor. So when these mats grew on the seafloor, what they would do is stabilize the rippled surfaces. So when a new depositional event occurred, the ripples were not eroded and are thus cast on the base of the new depositional event. And then the two bedding planes remain as discrete bed forms that are not amalgamated together. So this then continues as a process resulting in stacks of these sandstone bedding planes with no fine-grained interbeds, and is a definitive signature of past life that cannot occur in the absence of biological mediation. So this is potentially a really interesting biosignature for us to keep in mind when we're thinking about the search for life on Mars. And just you can compare it to kind of modern processes or broadly Phanerozoic conditions where we don't have mat grounds. If you get the deposition of sandstone on sandstone, the ripples are going to erode and the bedding planes are going to become amalgamated, resulting in a cross-section something like this. So you can tell that they're very distinct cross-sections, one with definitive evidence of past microbial life. So all in all, we can see that palimpsest ripples are potentially good biosignatures for us to keep in mind because they cannot be formed by abiotic processes. And they can occur when a mat is very thin, so they can even occur under biofilm mediation, so where it's not dependent on the presence of eukaryotes. And they're easily identifiable as macroscopic features in standard imagery, so you don't need a ton of analytical methods to identify them. But this is not to say there are no limitations, right? Firstly, this is restricted to rippled facies. You have to have ripples occurring in order for this to be identifiable in cross-section. But we know these are preserved on Mars, so this doesn't preclude the use of this feature as a biosignature. And additionally, the lithological criteria is narrow. You have to be able to identify the fact that this cross-section is comprised of only sandstone and no like clays or silts. But again, this is an ability we have to ascertain on the Martian surface. So with this in mind, we can kind of think about, well, then how would we detect them, right? I could go through by hand and look at all of the images coming out from the Mars Perseverance rover, but that's time consuming, right? So there's some things we need to consider in actually using this as a biosignature. First, there's a large number of images. We would ideally like to have rapid identification of these features, like as the images are taken, so we can identify target sites of interest for further analysis, because palimpsest ripples alone will not be enough evidence for us to be like, oh, there was life. You would need expertise in mat grounds and their impact on the sedimentological record. And of course, you want to minimize human error. So with all of these caveats in mind, I was kind of thinking, maybe the best way for us to approach this problem is to use an automated technique to identify palimpsest ripples in images of cross-sections. So this is exactly what I did, but I am not an expert in this. So I collaborated with the Visualization in Intelligent Systems Laboratory, or VisLab, in the College of Engineering at UCR, and worked with Dr. Birbanu and Padmaja Janalagada, who did a lot of this work with me. And the first thing I did was show them my data set from the Precambrian sedimentological record we had starting about 200 images of palimpsest ripples, because this project was born in COVID and I had no access to the field. So we started with this relatively limited data set and identified caveats of the data set that the program would need to overcome, including variable scale of images, variable resolution of images, and it would need to have the ability to account for extraneous features that are not related to palimpsest ripples, like plants, fractures, talus, dust, and shadows. And all three of these problems are problems that we would also have in like Mars, or images coming from Mars, besides the plants. So we started developing this program, and phase one, we developed the scene-aware perception augmentation using composite embedding for segmentation, or SpaceEgg, which uses Cora and SGE to identify images palimpsest ripples in images of outcrop. So these are just kind of a schematic of those different methodologies. If you're interested in the actual computer vision aspect of it, I encourage you to look at our paper, Jolla et al. 2021. And this first pass, their phase 1 development, was able to identify palimpsest ripples in cross-section. So you can see in the pink box, that is SpaceEgg, and it outperforms other state-of-the-art techniques for identifying planar features in imagery, and identifies palimpsest ripple bed junctions with an 89% accuracy rate. But 89% is not that great. We thought we could do more if we had more images. So once COVID restrictions lifted a little bit, we took 800 more images to kind of do phase 2 of this project, wherein we developed SpaceEgg 2.0, which instead used a combination of Aurora and BaseNet, shown here. This paper is currently in review. And this gave us a 92.32% accuracy, so much improved. And again, we see that it outperforms other techniques as well as our original SpaceEgg. So you can see it's much better at segmenting out the planar features that we are interested in and like really concentrating on the regions of interest. So to kind of conclude, palimpsest ripples are an important and definitive biosignature that should be included in target structures on Mars, and we have developed a technique for accurately detecting them using automated methodologies, which is potentially useful for our search for life on Mars. And just to say, our next steps, this project is not done. Our next step is to develop a classifier where we can feed through a bulk of images of different geologic features. It will be able to sort out between likely palimpsest ripples and non-palimpsest ripple cross-sections. And then those likely palimpsest ripple cross-sections will be fed into SpaceEgg 2.0, and that will give us a probability of the presence of the palimpsest ripples, and we'll also have the ability to classify morphology and other aspects of these features. So with that, I would like to thank my funding sources, as well as everyone who contributed to this project through taking imagery or ground truthing. And I would like to thank Ross and Jane Farger for access to the Nulpini Ediacara National Park on their property, and acknowledge that this land lies within the Adnyamathanha traditional lands. And again, there's a QR code for the Life RCN. Thanks.
Okay, fantastic, Rachel. Do we have any questions? See, this hand came up first, I think.
I was wondering, and first of all, thank you for a great talk. I was wondering, does anything about those ripples and texture or any other factors change over the course of the Precambrian? So like, are there any connections like major events like oxygenation or other things? And if so, like, can we infer anything? Can we infer any, like, make any past climate inferences for something like Mars?
This is a really good question, and talk to me after I finish my postdoc.
I will.
Anyone else?
So I'm wondering if there's any images from Mars that this can be applied to now, or we just have to reorient the cameras to sort of start doing that?
There are definitely images that this can be applied to. Like, that's kind of why I'm like harping on this biosignature, because it's like most of our imagery we're getting is of cross sections from the Martian surface. So yeah, once we have the classifier, we're going to start running them through. From what I've seen, just like looking at them, I don't see anything that would look like it, but it's an experiment we need to run.
I was just wondering if you guys were using any kind of like depth data for this, because it feels like these sort of in the images it looked very like quite 3D, and you know, if you have like 2 images, some kind of
parallax. So we did take that into consideration, kind of looking at the depth of the images, and it didn't really change kind of the performance of the program. So I believe it's incorporated into it, but it's not a huge aspect of it.
So, thank you.
Yeah.
Okay, we're going to take one more over here. Oh, Mike is itching to ask a question.
Hi, interesting talk. Kind of similar. Have you ever thought about applying this to maybe debated diagnostic biophases that are in the fossil record, just as additional Earth constraints?
I'm not quite clear on what your question is.
Just similar, at least other stromatolite or microbial systems that have debated sources.
Yeah, that's a really interesting question. No, so this is specifically developed just for this one feature. I think it is work that other people are doing that are not me. But yeah, there's definitely other computer vision programs that have been developed to identify similar features.
Thank you.
All right, we're going to let Mike ask a question. He's been working hard for us back here.
Okay, this is actually my question, not online. I'm just curious, if you did see something on Mars, what would you need to actually confirm that? Could you do it visually, or would you need sample return, or?
Yeah, that's a really good question. From my perspective, I think it's a first pass ID. I think it is a definitive biosignature, but I would never want to just say, oh, SpaceEgg 2.0 said there is a 99% chance and that's definitive evidence. I think, sample return or further analysis of that section would be needed to really definitively say anything.